question. So I know that Grobner bases are highly dependent on the order in terms of their efficiency.
Right.
So Faugere's algorithm, the F5, is it likewise highly order dependent, or does this minimality of the signatures, does it somehow cancel that out?
That's a good question. So yeah, good question. So yeah, I can mention that later on. Actually, if even for the fixed order for the polynomial, right, the signature order in his algorithm he doesn't have any choice. Choice on signature order. It's kind of only one order. Later on, we're going to introduce more general. So actually, you can pick a different order, signature for signature, compatible with whatever order you pick for the polynomial, and actually there will be big difference. So some order is better, much better. Okay.
Why is that? That always exists. Why does that always exist?
Exists the minimum one? Okay, that's a good question. We define term order, right? So we say that there's no infinite decreasing sequence of a term. We define that we're ordering. Okay, so
why isn't there two? Why is there just one? Couldn't we have two?
You mean minimum one, or why there's always minimum one? Oh, okay, there could be one.
Yeah.
There's no smaller one, but they're not compatible, right? Well, we define term order. We said any two terms you can compare which one's bigger, right? It has to be total order. Okay. Right.
Yes.
Okay. So it has to be total order. Where order means you don't have an even decrease sequence. You have to have a compatible with multiplication. That's a then we say it's a monomal order or term order. Okay. Okay. Then we say in our case we're not using Faugere's definition because that's very difficult to use. Because every time you compute it, you score something, you want to make sure it's a minimum, okay, right? It's difficult to use. So we just, in our definition, we just say, okay, you have a pair of polynomial. You have a pair UV, U is Rn, right? V is a polynomial, any pair. Okay, so we just say the signature of this pair, not this polynomial. Okay, which is the signature of this pair is just the lead term of U. That part we say that's a lead signature. We just use it in that sense. So this is a very, very flexible. You can use it. For any pair say have signature. So no problem, right? Okay.
So there's no hypothesis on.
No condition.
No condition. No relationship.
Yeah. In computation work, you'll see it in a moment. So the UV will come from ideal module, right? So but the definition just say any pair the signature of that pair. Okay, right? There's nothing involved in there, okay, right? Okay. Now we're going to also define reduction, okay? Reduction, just the polynomial have to do a total reduction, just reduce the lead term, okay? For a pair, they come from module, we're going to define reduction in a similar way. Basically, I'm trying to, okay, let me write it down. Okay, so when I do reduction, look at the equation 1 there. I'm going to use V1, V2 are polynomials. U1, U2 are those tuple, okay? So basically the idea is that I'm going to use V2, try to reduce V1, the polynomial part, I try to reduce the leading term, try to compute the CT, right? So try to cancel the leading term of V1, well, if V2 is non-zero. If V2 is 0, you cannot reduce that part anyway, right? You just reduce the U part. Okay, so suppose V2 is non-zero. I try to, if the leading term of U2 divides leading monomer of V1, you can do this reduction, okay? Otherwise, you cannot do reduction. So that's a low mode reduction, okay? But there's one more catch in there, that's condition 2. Say, well, if you do reduction, I want to make sure the TU, look at the U part, the TU2, right? That's a signature. The leading term of that one, should that be bigger than the leading term of U1? Should be most of then I allow this reduction. If the U2 part becomes T times monomial, if the order gets bigger than U1, then I don't do this reduction. That's not allowed. You have to be at most of one, I perform this reduction. So this means that when I do reduction, use P2 to reduce P1. The polynomial part, I try to make it smaller. But the signature part, the U part, I want to keep them the same, or smaller, okay, right? I don't want to increase the U part. That's the ideal for when you have a pair of reduction, right? That's easy to remember, right? Okay, so of course, so we say total reduction. This reduction is called regular. if the signature part, like after reduction the U, right, that part, the signature doesn't change. Okay, because this is guaranteed either equal or smaller. If it doesn't change, we say it's regular reduction. The signature part didn't change. If it gets smaller, this means the polynomial gets smaller, the signature gets smaller, both get smaller, then we say that's a super reduction. Both get smaller. Okay, so regular reduction, super reduction. Now when V2 equals 0, the polynomial part I cannot reduce, okay? We just use the signature part I can reduce U1. Then I can reduce that part, then say it's also a total reduction. Okay? Basically, that's also called super. That's part of super reduction. Basically, say signature P1 remains the same under regular total reduction, but it becomes smaller under super total reduction. That's all I want you to remember. Okay, so now, okay, you have now introduce a pair and introduce reduction. So now, suppose I give you a set of polynomial in there. I'm going to work in this big module M. So you see that the pair UV. So now the combination of U, right, with G equal to the polynomial V, then we say that the UV would be that module. In particular, like E1, G1, right? That is in that ideal in that module. So E2, G2, so E basically indicates position, right? So those are the actually generators, those modules, the generators. Okay. So this module actually, this means I'm going to get a generator polynomial. This means I give a generator for that module. I try to complete the Grob basis for that module. Okay. So yeah, start with that generators. I'm going to define Grob basis. So now suppose I take subset of pairs from the module M. We call it Grob basis, or I'm using kind of other words, strong Grob basis, just indicates slightly different. Okay. A strong Grob basis for M for this big module. If every pair in this M, okay, is reducible by some pair in G. So this is the definition is the same as the Buchberger's definition, right? But I'm working in a more bigger module, and including you'll see that this includes reach everything is in here. So definition, right? For every this infinite M is infinite, right? Everyone you have to be co-reducible by something in G. Then we say G is a Grob basis. So this is a kind of very natural definition. If you look at other papers, like every other paper in the definition of even Grob basis is not very natural anymore. They try to fit their argument to define Grob basis. So I think this one is a Buchberger's generalized, it's a very natural one. Now, okay, if you have Grob basis, okay, so that module M, you pick a, suppose you compute the Grob basis. This is what Grob basis tell you. Well, if you suppose G is a strong Grob basis for that module, then what I do is that if you take all the polynomial, all the pair where the VI is 0, there are VI 0, then the corresponding UI part I can collect them, call that T0. So there are lots of them. The V part is 0. Then the U actually is a Suzuki, right? Suzuki. I collect all those together. Actually, those part will be a Grob basis for the Suzuki module. So likely Grob basis for the module. Now the V part, there's some V part, some are 0, some are non-0. Okay, you collect all of them together. Of course, 0 just move away. Then the V part is automatic Grob basis for the ideal. Okay, so remember this reduction, actually you're working with the ideal part, right? Do reduction for S, we will talk about for S pair or S polynomial, all based on the V part. Right? So if you can find such thing, right? You get a Suzuki module, get a Grob basis for the Suzuki module, get a Grob basis for the ideal at the same time. Okay? Let's see. Okay. Let's see, I have to time, okay, make sure I don't get too slow. When did I finish? 12, right?
Yeah, about 5 or 10 minutes.
Okay. Yeah, I think maybe I'm maybe slow. Okay, let me try to get this clear. I wanna compute like a S polynomial. Let me see this page. Okay, I'm gonna try to form. Okay, let's see. So from two pair, right? Just like the polynomial case, I try to form well, pair may not be Grob basis. I'm trying to form a new pair so I can add to the set. I can get new one. I can get Grob basis. So the ideal is that I use the V1, V2 part, just the same way as we do for S polynomial, right? So see we do S polynomial, that's the things we do, right? The V1, T1, V1, right? C, T2, you put S polynomial the way you compute the T1, polynomial T1, T2, LCM of the term of V, okay, the polynomial. So similar, so you don't have to memorize, just think about the parallel. Okay. Now for the pair part, so this is translated into pair, right? You have T1, T2, you do the polynomial part, and you do the U part. Well, the U part maybe depend on the T1, U1, T2, U2, what the term, which one is bigger, okay? Because we form this one, some term will get bigger. So say T, the T could be max leading term of U1, U2 part. So, or equal to one of them, some of them. So if I create that one, you try to compare those leading term, okay? If the leading also coefficients, if there's a leading monomial, suppose if I create such a polynomial, if the leading term equal to this T, right? If I do reductions, that's C. C is defined by a polynomial. So if that's equal to the maximum term, that means maximum term don't get reduced. Then we say T actually is the signature of joint. J means the joint signature of P1, P2. So the maximum T, okay, for joint signature. And this polynomial, this pair Ti, Pi, well, it's one of them. Okay, so then we call that the joint pair of P1, P2. So maybe it could be T1, P1. This pair, right, just P1 times the monomial. That pair, that's the biggest one. The determinant biggest one, right, on that one. So we call that the joint pair of P1, P2. So joint pair, I don't actually do the calculation yet. Later on, I do calculation. So but at the moment, when we talk about J pair, it's just joint one. It's one of the pair times the monomial. Okay, you get biggest leading term. So we call that J pair. So when we create an S polynomial, actually corresponds to that top one. You do calculation, you get S polynomial. So it's slightly different technology. So we define well, this condition that leading monomial keep the same. Just if they do that, the complete other one, the leading term gets small, can get cancelled out. Then we don't define joint pair. So this means we don't use that joint pair. Okay, so sorry about lots of definition. So here's the theorem. So after all this definition, right? So because we want to have a characterization of the strong Gao basis, and also this characterization should tell us how to know the useless pair, some pair, right? Some joint pair. I want to know they're going to reduce to zero or not without doing reduction. So let's think about this one. So you have this generator give a G, right? So suppose you have G of a subset of a module, and those matter condition, you do the matter condition module. So then you say, okay, I want to know G if G is a strong Gao basis for M or not. That's the definition, right? I want to know if it's a Gao basis. Well, by Buchberger theorem, basically say if Buchberger theorem says that okay, I want every J pair of G can be reduced to zero by G. Okay, reduced by zero by G, just in the usual sense, right? Just do top reduction. You want to make sure everyone reduces zero. That's the Buchberger theorem. Or generalize here directly. Okay. So that's one, but you have to do reduction. Okay, you have a joint pair, you have to do reduction. So that's expensive to do. Now in our original version, we have the condition C. So okay, every J pair can be eventually super top reduced by G. Let's say that's a non-sentence. Okay. So this means that I'm going to try to give J pair. I'm going to try to use G to reduce. We're going to perform regular reduction. Okay, we're going to keep reduction, reduce, until I cannot do top reduction. I cannot do super top reduction. Oh, cannot do regular top reduction. Regular means I don't reduce the signature. Okay, so reduction. Well, now I check if it can be super top reducible. Means that I can still do reduction, but the signature will get smaller. That part, if it's super reducible, then I say that's called eventual super top reducible. Otherwise, it's not super reducible. So this condition C means that, okay, you have a J pair, I'm just do regular reduction. If it becomes super, that pair I'm okay. I don't have to reduce to zero, okay? If I get to pair L, it's super top reducible now, but not regular top reducible. Then that pair, I assume more emission, I don't have to perform the remainder of reduction, so that's saving in time. Okay. So that's better than C condition is better than B, but I still have to perform reduction though. Okay. So for every J pair you have to do that, and if you can check that one, it's a group basis. So all this condition correct. Condition D. Okay. Every J pair is covered by G. Okay. Well, let's see what I mean by covered by G. So that's where I want to explain. That's a best condition. Okay. So how do we say every pair covered by G? So okay, let's say before I say that, so that's condition D, right? Say okay, do we have a group basis? Well, the implementation we're going to use condition D. Okay, even though we don't know yet what it is, right? But so condition D. So if I check that condition D, then I know it's a strong group basis or not. So now let's say what do we mean by covered by G? So you have a pair, let's say J pair, you form it okay from there. Now I want to check. We say it's covered by G. If there is a pair in G, so I just look at the pair in G. I want to see if there is a pair such that the leading term of that U1, okay, divides the leading term of this U start with. Okay, so if the signature divides, you have some T, monomial T, right? Divides this, you get that together. Now I check the T times B1, this polynomial part. Okay, because I want to match the signature. I want to get the signature, the same signature times T. Then I look at the polynomial part, T times B1. See, I want to make sure that's strictly smaller than the polynomial in V, the term of V. If we can find such polynomial in G, then we say that pair P is covered by G. Okay, so this one is you don't do reduction, just check, right? Just check the divides or not, then check it smaller than that. So then that's called covered by G, no reduction involved. Okay, so you want to make sure that's condition C said that you have a single form pair. I just form J pair, right? Then actually each J pair is not covered by G. Just check this condition, right? If it is, I'm done. So no reduction involved. Okay, so that's the condition. That's the theorem. I think because in your original version, your paper in 2010, in the original version, we didn't have D. People read it. Still people include that paper, include the older version. That's condition C. So still include that one and try to include. But this condition, I think we put it. I think 2011 we put that version there. But I think people still didn't realize this condition actually is much better. It's very easy to use. Okay. So this actually, because that condition tell me, right, because pair reduce zero immediately, right? I don't have to do reduction, but does any of the pair J pair satisfies condition D, right? If satisfies the condition D, it can be discarded. So that's how you make the useless pair, useless polynomial. Okay. Including whatever people talk about the criterion, right? Talk about in the literature, is implied by this. Okay, so just a quick remark. Okay, so we do implementation. Okay, kind of implementation. Well, this vector U, that's a huge you need a huge amount of information storage. Okay, memory to store because each polynomial is huge. You have lots of polynomial, right? So in practice, actually, we only store the leading term. If we don't need the group basis for the Suzuki, right? If I just want a group basis for the ideal, I don't have to complete the Suzuki, the whole vector. I just store the leading term. Okay, that's called signature. That's the A5. Okay, A5 you just store the leading term. So just store them, and then all the definition in my theorem just involve the leading term. Okay, I don't care about the other term, right? So everything you can still perform all the computation. Just store polynomial V and the signature the pair whatever you compute, right? That's the signature. So then you do computation, right? You pair whatever do reduction. Okay, so that you just go from it, the signature. And also there's previous Suzuki. You have a pair, you have another pair, there's previous Suzuki. You store that signature U in there. So you don't do any computation, you get the signature in term. That's in your module. That will save lots of time also because anything divisible by the in term of U here, then you store them away immediately because if this one is your G, you have a Suzuki in your G. So you have another pair, the leading term is divided by this U. Because zero, this is polynomial part is zero, it's always much more than your term. So if this one is in your T, then if you have added joint pair, and the leading signature divided by this one, that's automatically covered by this one. So yeah, store them away. Okay. Anyway, that's the kind of criterion. There's one more thing before I can finish. So in literature, you see that if you try to read paper, several people try to say, okay, I try to prove F5, try to prove it's correct, even correct, right? Say I always commit basis, it's correct this, and also finite termination. Actually, there are quite a few people who try to prove them. Actually, almost all of them has a problem with the proof. In our paper, we actually try to point out which part is wrong. Okay, so even the recent ones, their paper proof doesn't, it's not quite right. Okay, actually, our paper then in 2010, after the paper in Beijing, then he found actually good argument, proof. Actually, but that paper actually is pretty good. The trouble is that he didn't write it well, so they will get published. People don't quite understand his paper. So here was a counter example. If the term order is not compatible, then the computation actually may not finish in final time. So he gave example, but in the 2011 the paper said, okay, any order you can finish final time. That's the proof. Even there are some other problems too. Anyway, we can now actually use condition C. You can give a proof much simpler. Okay, so in the new version we have that proof in there. Anyway, so let's see. Okay, let's see. I want to mention there are questions like we said. Okay, if you fix order on M, you can have a different order on the sixth order. This is where I try to give. So, like if you use a position on the Rm, use position over term order. Actually, that order, if you do that one, that's kind of give you incremental argument like F5. So F5 corresponds to use a part order. Okay, and then if you use a term over position order, this means you use the total degree. Well, like okay, so here I have more condition. Well, okay, like this one. G1, G2 means that you use the I say this term, this one that term. If I'm talking to G, right? Look at the polynomial of the degree. Use the graded one on that part. This is called the graded order. In this one, so you have a suite. You have kind of lots of choice in there. So this is kind of graded one. Use the polynomial part. So plotting G, replace the EI by GI, right? Look at the polynomial. Look at the degree. Decide that on graded order for G1, G2. Then we have a table say compare. Okay, so just very quick. So I fixed term order for the polynomial part. Now I vary the secret order. I see which one is better. We do some example of polynomial system, small comparison. So if you see that G1, G2, these are base one. Okay, so it's much faster than G2. Use that secret order, like point order position like F5. Our first paper, incremental one, G2B, that's our first paper, use the incremental one. Usually it's much slower. Okay, like if you use A5, correspond to the first column. So G1, G2 use graded order, so you can pick a signature order, actually the computation is much faster. So I think that this just indicates that you should pick this graded order for the signature part.
Does singular have F5 in it?
Singular, initially I think should be in there, yeah.
Okay.
Because F5 came out 10 years ago, right? Yeah. Actually, it should be in there. I don't know. I'm not sure. Yeah, because I use sometimes, but I didn't pay attention. Yeah. Anyway, that's the kind of from here experiment. So we talk about ideal. We try to when we have freedom to pick signature order, that's the order you should use. Okay. Anyway, just conclude. So there are still lots of problems to work on, right? So like if you try to solve common system, I think the way I present it is kind of very theoretical. So if you try to apply to big system, okay, so if you have a polynomial system like a few thousand variable physical equation, that's still a big challenge. So, but if you encrypt the system, the way you do encryption, right? It's there's kind of structure, go top down, do computation in order. So how can you say you cannot say a particular system and try to commit probations? You cannot do it. So somehow explore local information like a structure. How can you do that? A structure. How can you speed up computation in some sense? I don't know exactly how to do it, but sometimes there's structure. How can you speed up? That's kind of major challenge. Yeah. So also when you do global computation, there's complexity issue. So because all the time you compute this computation of the G, right? The U coefficient part of the polynomial question what's the degree? How high you have to go. Try to characterize theoretically. That's related to the regularity problem, like Castanova or Mumford regularity. There are actually lots of people working on that area. So, but this, just I think it's still a good area to work on. So one of my students actually she's working on that part. Also, some structure of generic polynomial system. There are lots of theoretical questions there. Okay, so that's still like a challenge in this area. Okay.
Thank you very much. Any questions?
Yeah, question. So I know that finding a Groebner basis is X space complete, but with these reductions and these cancellations, I've never studied that proof.
Okay.
And is there any hope for reducing the complexity class? You know, getting rid of that X space complete requirement by using those memory cancellations, or is there something inherent in the structure of the Groebner basis that makes
Okay,
it?
there's I think the trouble is that this polynomial, when you have involve more variable, you store the polynomial. Polynomial itself is big, right?
Yeah.
That's the main trouble. So how do you get rid of that one?
I see.
Okay, how do you represent a polynomial? Let's say use a straight line program, for example. If you can do that one, probably there's hope. Okay.
I see.
You don't actually write down all the terms, but then everything doesn't work, right? Because we depend on term, right?
Yeah.
Yeah. So that's a good question. Yeah. Yes.
So you computed the first decision module. Why not do this for the whole resolution of the ideal?
Yeah, this also works. You start with a polynomial, right? You start with a vector. You try to compute solidity, right? This works same way. Okay. Yeah.
So just to piggyback on your first problem with structure, many of the examples you showed in your timings have some group action that is working. And Faugere has a new paper in the latest ISAC, 2013, on how to use F5 with group actions.
Okay, some summation polynomial or something.
Yeah,
okay.
That's right. So, so it'd be interesting to see whether the techniques from his latest paper there would cooperate nicely with your algorithm.
Yeah, that's a good question. Yeah, I haven't started that paper yet. So yeah, good question. Like this kind of structure, yes. Like invert under a certain group, right? Okay.
So where can we get your algorithm? Is it implemented in singular, or can we, just to try it out and experiment, is it implemented where we can download it, or still theoretical?
Let's see. I think my students getting implementation. That's quite a few, 1-2 years ago, right?
Okay.
Somehow around it anymore. He's in SAS, right?
Right.
Okay, so, but there's other people like I think Stillman, his postdoc, did implementation on their own stuff, right? So I think if you check ESA paper, they should mention if they put it on somewhere.
Oh, okay.
Okay. There's also Ada, she made the German group, right? They made have some implementation, so it's incorporated all the ideal. Okay. Yeah.
Thank you again.